Okay, moving on to section B. Section B, let's start with question number 9. So question number 9 tells us that both carbonate and lead sulfate are insoluble in water. So part A asks us to state the suitable method of preparing such salts, since both salts are insoluble. The suitable method is precipitation, sometimes called double decomposition. That is a suitable method. Moving on to question B. So question B asks us to describe and outline how pure dry lead sulfate would be prepared and collected, starting from lead carbonate and selecting from the given reactants, which is lead carbonate solid, dilute sulfuric acid, dilute nitric acid, sodium sulfate, and distilled water. So let's go through this step by step as a full method. So step number 1, lead carbonate does not dissolve in water, so we cannot react it directly with the sulfuric acid to get a clean reaction. Since lead sulfate is also insoluble and would cause the lead carbonate stopping the reaction. So instead, we first dissolve the lead carbonate using dilute nitric acid, since lead nitrate is soluble. Add excess lead carbonate solid to the dilute nitric acid and stir until no more dissolves, forming a solution of lead nitrate. Step 2, filter the mixture to remove the unreacted excess lead carbonate. Since we added it in the excess to make sure that all the acid was used up, this leaves us with a clear filtrate of lead nitrate solution. Step 3, add this lead nitrate solution to dilute sulfuric acid or to a solution of sodium sulfate. A precipitate of lead sulfate forms immediately because lead sulfate is soluble. Step 4, filter the mixture again to collect the lead sulfate precipitate. Step number 5, wash the precipitate with distilled water to remove any soluble impurities such as the leftover sodium nitrate or nitric acid. Step 6, dry the precipitate, ideally between sheets of filter paper or in a warm oven to obtain pure dry lead sulfate. That's a full 6 marks method right there. Moving on to question part C. Part C asks us to explain why the lead salts are not prepared by the acid alkali titration method. The reason is that most lead salts, including lead sulfate and lead carbonate, are insoluble in water. The titration method only works for the prepared insoluble salts, since it relies completely dissolving both the acid and the bases, and then evaporating the solution to crystallize the salt. Since lead salt does not stay dissolved, this method simply does not apply. Okay, moving on to part D. Part D asks us to state the chemical test for the sulfate ions. So the test is to add dilute hydrochloric acid followed by barium chloride solution to the sample. If a white precipitate forms, this confirms that the presence of sulfate ions, since barium sulfate is insoluble and forms this white precipitate. So that's question B9 complete. 10 marks, just like that. Now let's move on to question B10, which covers the bond energy and enthalpy changes. Alright, solution B10 gives us the equation: hydrogen gas plus chlorine gas produces 2 hydrogen fluoride gas. Part A asks us to construct an equation using structure formula showing the bonds. This means instead of writing H2 plus 4 plus F2 arrow equals to 2 HF, we draw each molecule showing the single bond between the two atoms. So H, you have the bond with another H, plus F with another bond F, will give us two separate F with separate H with F molecules, each showing a single bond between the hydrogen and the fluorine atoms. Part B refers to the bond energy table, which gives us H connected to H bond plus 436 kilojoules per mole of F to F bond, as plus 138 kilojoules per mole, and H to F bond as plus 562 kilojoules per mole. Then part B, I asks us to calculate the enthalpy change, which is delta H for the reaction. So let's walk through this step by step. Grab your pen and paper. Please, if you haven't subscribed, please subscribe. If you haven't liked, please like. And please, if you have any question why you feel you are stuck in this past paper video, please comment so that I can help you or give you exactly same number. Make sure to state the question number and the exact part of the question, then state why you're not understanding. Don't just leave the don't just come out and comment the exact problem. No, I don't understand why the answer is coming from. How can you comment like that? How will I know that you're watching this question number, this or question number? So please make sure you leave the question number and the part of the question so that at least when I'm responding to you where you have the question, I can know exactly where to go. Thank you. Now let's continue with our calculation. Alright, so step number 1, calculate the energy needed to break the bonds in the reactants. We break one H to H bond and one F to F bond. That's 436 plus 138, which gives us 594 kilojoules per mole absorbed. Step number 2, we need to calculate the energy released when the bonds in the product are formed. We form two H to F bonds, so that's 2 times 562, which gives us 1124 kilojoules per mole released. Step number 3, calculate the delta H using the formula energy absorbed minus energy released. That's the 594 minus 1124, which gives us minus 530 kilojoules per mole. Since the answer is negative, this tells us the reaction is what? Exothermic. Please, if you haven't watched a video on how to draw these energy profile diagrams, please do comment in the comment section so that I can send you the link of a video on how to draw these diagrams. Or you can watch this video where I will teach you how to draw it as well. Okay, meaning it releases what? Energy overall. Okay, moving on to question B2. So question B2 asks us to draw an energy profile diagram for the reaction, labeling the reactants and products, delta H and the activation energy as EA. Here's how to picture this diagram. So on the vertical axis, we have the energy, and on the horizontal axis, we have the progress of the reaction. Since reaction is exothermic, the reactions start at a higher energy level, or in other words, the reactants will be what? On top. And on the left side of the graph, the curve then rises up to a peak, which represents the activation energy. That curve simply represents what? Activation energy. And before dropping down to a lower energy level on the right side where the product sits. So when you're doing the diagram, the energy profile diagram for the exothermic reaction, just know that the reactants are always on top, then the product are always at the bottom. Or in other ways, I like calling it as a normal one, because we know that the product should always be at the end. So which means the opposite is true for the endothermic. The products will be on top, the reactants will be at the bottom. You have learned one or two things there. If you have learned something, please comment and let other people know what you have learned in the video. Alright, so moving on to the question. The activation energy, which is EA, is labeled as the vertical distance from the reactants up to the peak of the curve. Delta H is labeled as the vertical distance between the reactants energy level and the product's energy level. In short, the distance between those two, that's where the delta H is placed. Alright, moving on to question C, which is access to definitions. But C1 asks what is meant by the activation energy. So activation energy is simply the minimum amount of energy that colliding particles need in order to react successfully. So activation energy is the minimum amount of energy that colliding particles need in order to react successfully. Then part C2 asks what is meant by the term bond energy. What is meant by bond energy? So bond energy is the amount of energy required to break one more of the particular covalent bond in the gaseous state. Moving on to part D. D tells us the reaction is then catalyzed and asks us to show EA2 for the catalyzed reaction on our diagram. When a catalyst is added or is used, it provides an alternative pathway with a lower activation energy. So on the same diagram, you would draw a second curve with a lower peak than the original one, meaning that just beneath it, you draw the label. Label this lower peak as EA2, showing that less energy is needed to start the reaction when a catalyst is present. And that's question B10 complete. 10 marks. Now let's move on to question B11. So question B11 tells us that a learner was provided with compound X, dilute hydrochloric acid to prepare gas Y, and that gas Y is used by plants during photosynthesis. Since the gas is used in photosynthesis, this tells us straight away that gas Y is carbon dioxide. And since we are using dilute hydrochloric acid to prepare it, compound X must be a carbonate, mostly calcium carbonate, sometimes written as marble chips or limestone. Okay, part A asks us to write the chemical formula for compound X and gas Y. Compound X, calcium carbonate, is CaCO3. Gas Y, carbonate dioxide, is CO2. Then part A asks us to construct a balanced chemical equation for the reaction of compound X and dilute hydrochloric acid. So let's build this step by step. So calcium carbonate reacts with hydrochloric acid to produce calcium chloride, water, and carbon dioxide gas. The balance equation is CaCO3 plus HCl gives us CaCl2 plus H2O plus CO2. We need two hydrochloric acid molecules to balance the two chlorine atoms in calcium chloride. Then moving on to question B. Question B asks us to describe the chemical test of gas Y in the laboratory. Describe the chemical test of gas Y in the laboratory. So the test for carbon dioxide is to bubble the gas through lime water. So the test for carbon dioxide is to bubble the gas through lime water. The lime water turns cloudy or milky white. This confirms the gas is carbon dioxide. Moving on to part C. Then part C1 asks us what method is used to collect a dry sample of gas. Carbon dioxide is collected by downward delivery, sometimes described as a collection over a trough using a gas syringe. But more specifically, for a dry sample, you would pass the gas through a drying agent such as concentrated sulfuric acid, then collect it by downward method delivery. Okay. Moving on to question C2. So question C2 reads or asks us why this method is suitable for collecting gas Y. Why this method is suitable for collecting gas Y. This method is suitable because carbon dioxide is denser than air. So it sinks and displaces the air downward and out of the collection vessel without needing to dissolve in or react with water. Since carbon dioxide is slightly soluble in water, which is why we avoid collecting it over water if we wanted to dry sample. Then move on to question D. Question D asks us to state the two commercial uses of gas Y. Carbon dioxide is commonly used in fancy drinks to give them their bubbles and as a fire extinguisher since it is denser than air and doesn't support combustion. So it's smoother. It puts off the fire. 12B. Question 12B, our final question on alkenes. Question B tells us that alkenes are a homologous series of separated hydrocarbons and can exist as isomers. Then part A asks us to define the term homologous series and isomers. A homologous series is a family of compounds with the same general formula, similar chemical properties, and which differ from one member to the next by CH2 unit, showing a gradual change in the physical properties such as boiling point. Isomers are compounds that have the same molecular formula but different structure arrangement of their atoms. So that's the definition there. Isomers are compounds that have the same molecular formula but different structure arrangement of their atoms. Then moving on to question B. Section B asks us to draw any two structures of isomers of pentane, which is C5H12. So pentane has three possible isomers, but we only need two. The first is a normal pentane, a straight chain of 5 carbon atoms, each bonded to each hydrogen atoms to satisfy their 4 bonds per carbon. So for we know that carbon to be stable, it needs 4 bonds. The second could be methane butane, 2-methane butane, which is a 4 carbon chain with 1 methyl branch coming off the second carbon. When drawing these, make sure every carbon atom shows 4 bonds in total, whether to hydrogen or to neighboring carbons. Then part C is about the fractional distillation of crude oil, shown in the diagram with a fractionating tower, where crude oil enters at the bottom, heated above the 400 degrees Celsius, and the different fractions are collected at different heights, labeled as gassy, petrol, paraffin, substance X, evaporating oil, wax, and substance Y at the very bottom. Then part C1 acts as C to name the substances collected at X and Y. Looking at the position in the tower between paraffin, and the lubricating oil, substance X is diesel. So substance X is what? Diesel, sometimes called gassy oil. And substance Y collected at the very bottom below wax is bitumen, sometimes called residue. Sometimes it's called what? Residue. Then part C2 acts as for one use of substance Y. Butane is commonly used for surfacing roads or roofing materials. Then we're going to question D1. Question D1 asks what we understand by the term cracking. What do we understand by the term cracking? So cracking is a process of breaking down large hydrocarbon molecules into smaller, more useful molecules using the heat and sometimes a catalyst. So that is what cracking is. Then question 2, D2 shows us that 1-octane COH18 is obtained alongside propane in the cracking process as the only products and access to construct an equation for this process, including the condition. Let's work this out step by step. We need to figure out what large hydrocarbon breaks down into octane and propane. We add the carbon atoms together. Octane has 8 carbons and propane C3H6 has 3 carbons, giving a total of 11 carbons. So the starting hydrocarbon must have 11 carbons. For a saturated alkane with 11 carbons, the formula would be C11H24, following the general formula for alkanes. Let's check the hydrogen balance. Octane is C8H18 and propane is C360H6. Adding these together gives us 18 plus 6, 8 18 plus 6, which is 24 hydrogen matching the C11 and H24 exactly. So the equation is C11 H24 gives us C8 H18 plus C3 H6. The conditions for this cracking process are heat and the presence of a catalyst. So you will write the above arrow. So you need to write about the arrow, the catalyst and the heat about the arrow. That brings us to the end of question B12, final question. We have 10 marks, and that completes our full walkthrough of the chemistry 57 paper 2, covering section A and 4 questions from section B. Make sure you go back over every section that felt tricky, especially the calculation questions and the equation building steps, since those are where most marks tend to slip away in exams. Keep practicing and you get more competent with every paper you work through. This was your tutor, Robert Mtare. I hope you have learned one or two things. If you have do so, please subscribe, like, and leave a comment. I would love to know which paper you want me to do or which question I should do. Make a video or just leave a comment there indicating the question number and the year, where the question came from. Then I'll be able to help you with the passionately. Or if you can go a bit further, you can WhatsApp me on the number 0968032811, where we do our online teachings, whereby we go deep in this topic, not just answering past papers, but we go deep. We teach the entire topic, then we answer past papers, so you solidify your standing on each. No, at Mtale TV online tuitions, time is very cardinal. Time is very cardinal, so we don't waste time on Mtale TV. We only teach what comes in this exam, which is in the syllabus. Thank you for watching. If you haven't subscribed, please subscribe. If you haven't liked, please like. If you haven't comment, please comment. If you haven't joined our online tuitions, please join our online tuitions. This is Robert Mtale, your tutor. Thanks for watching. Bye bye.